So, problem 3 says that a triangular pulse is moving at 1 centimeter per second as shown here. One end of the rope is fixed to a wall and the other end to a ring which can move on a frictionless pole. Assume that the wave is reflected from the ends without any loss of energy, obviously, because without that we can't work. Also, we have to check which of the following statements are true. The pulse is inverted at t equal to 5 and upright at t equal to 8, or an amplitude of 2 cm is observed at 10n plus 2 seconds where n is a whole number. The total energy is in form of kinetic energy at 10n plus 7 seconds where n is again a whole number, or all of the above. So again we are given a system in which there is a fixed wall at one end and there's a
open end.
Okay, and there's an open end at the other end.
The properties of fixed end and open end will be used to solve this kind of problem.
Correct.
So
the most important thing about a closed end, about a fixed end and an open end is what?
Yeah, at the open end the phase doesn't change when the wave hits the open end, but when the wave hits the closed end, the phase changes by pi radians.
Right.
So these properties have to be utilized. If you observe clearly, the pulse, the amplitude, the maximum point of the pulse is at a distance of 2 centimeters from the open end, and the speed of pulse is 1 centimeters per second to right.
Okay.
So within 2 seconds the pulse will be hitting the open end.
Right.
But let's just see how the pulse is after 1 second.
Okay. And why are we doing this exactly?
Yeah, so that you can easily understand how the amplitude changes when it hits the open end.
Okay.
So this is the open end.
Okay.
After 1 second.
Right.
This is 1 centimeter. Now just imagine when this part of the pulse is slowly moving inside, since this doesn't absorb any energy, whole of the wave will be completely reflected inwards without any phase change.
Correct.
So after 1 second there will be an incident wave and also a reflected wave.
Correct.
The reflected wave is same as the incident wave but with opposite velocity.
Right.
So both the amplitudes add up.
Okay.
By the principle of superposition.
Right.
So we get A1 plus A2 is 2 centimeters.
Right.
At t is equal to 2 seconds.
Correct. Okay.
And the phase doesn't change.
Right.
It is upright.
Now we can already see that since there is a wave which created another wave in a second, and now you can make sense of the fact that there is the answers, the options have expressions of the form 10n plus 2, because a lot of things will keep on repeating here.
Exactly.
Right.
So after 3 more seconds it will be moving on to left.
Right.
So it will be somewhere here. But it is upright in that at 5 seconds.
Correct.
And it is inverted at 8 seconds. If you go on see, it will be inverted.
Right.
So option A is wrong.
Okay.
And as we have already discussed, the amplitude is 2 centimeters at t is equal to 2 seconds.
Right.
But if you see, the total distance between the open end and the closed end is 5 centimeters.
Correct.
This is 5 centimeters. So for a pulse which starts at the open end,
right,
which goes to the closed end and again to come to open end, it takes 10 centimeters by 1 centimeter per second. So it takes 10 seconds.
10 seconds, correct.
So after every 10 seconds, the amplitude repeats itself.
Right. A new wave will be generated after every 10 seconds.
Yeah.
Right.
So you get amplitude 2 centimeters after every 10 plus 2 seconds.
Right.
So option B is right.
Correct.
So if you observe at one instant when it is about to hit the closed end.
Okay, the fixed wall. Right.
It is this way.
Okay.
Now when it is slowly moving inside, this fixed end's property is to invert the wave. So what happens is, when half of it is inside.
Right. Because we discussed that at a fixed end, there is a phase difference of
pi.
Right.
So this is the incident wave when half is inside.
Right.
And this is the reflected wave. This is the reflected wave.
Correct.
So both of them cancel out to give no wave.
Exactly.
It is a horizontal line.
This is only for the instant where that wave will be near the fixed wall, because
Yeah.
at the next
When
instant there will be a wave.
half of it is inside.
Right.
So it tries to reflect half of it by a phase difference of pi.
Correct.
So when there is no strain in the string, there won't be any potential energy.
Right.
The total energy will be manifested in the form of kinetic energy.
Right.
And this happens at the 7th second, because it reaches the open end at t is equal to 2 seconds.
Right.
And it needs 5 more seconds to reach this end. So at 7th second it reaches the closed end for the first time.
Right.
And similarly it repeats itself after every 10 seconds.
Correct.
So total energy is in the form of kinetic energy after every 10 and plus 7 seconds.
Okay. So because the total energy is in the form of kinetic energy when the pulse is at the open end.
At the closed end.
At the closed end. Okay.
So B and C are right options.
Okay. So basically, since there is no displacement of the particles, so that is why potential energy is
potential
zero.
energy is zero.
Okay. So that was problem 3, and we saw that we were given a triangular pulse, and we were given a system which had a closed fixed wall at one end and an open end. So we found out that the pulse will repeat back and forth between the two ends, and we found out patterns for when it will generate a new wave and for when it will be closer to the fixed wall, which makes it seem like the amplitude 0, but obviously the next second there will be a wave, because the wave has only been shifted by a phase difference of pi. It has not gone away. It's just that the reflected and the incident waves cancel each other out at that point of time. So this was problem 3, very important concepts here, and this actually will make you very comfortable with working with incident, reflected and transmitted waves. So this was problem 3, and we'll move on to the next one now. So problem 4 says that a rope of mass m and length l with uniform cross section is hanging as shown in the figure, and we have to find the time required for a transfer wave set up at the bottom to reach the top. Okay, strange question actually, and not a lot of information given, so obviously it has to be conceptual.
So let's see how the velocity varies with respect to position.
Right.
See, we know that velocity is under root t by mu.
Okay. I already see that there is the force of gravity to take control.
Exactly, yeah.
Right.
So suppose you consider a point at this height.
Correct.
The tension acting at this point is different compared to a point at this height.
Right.
So we need to use a technique of integration here.
Exactly. In fact, that is the concept of this behind this question.
Exactly.
And if you can figure that out, this question becomes very meaningful to us.
Exactly.
Right.
So let's find out the function of tension as in terms of x.
Right.
So take an element of length dx
Right.
at a distance x from the bottom. So your tension is mu, which is mass per unit length,
Right.
into x into g.
Correct. M into G.
Yeah. So this is the tension acting at that particular height.
Right.
Plug this into the velocity equation.
Okay.
You get velocity as under root gx.
Okay. So now we have an expression for velocity as a function of x. Right.
So velocity is nothing but dx by dt
Correct.
is equal to under root gx.
Right.
So get the terms on one side and start the integration.
Right.
Dx by root x is
Okay.
equal to dt into root g.
Right.
Now integrate from 0 to L
Right.
on the left hand side and 0 to t on the right hand side.
Correct.
So what you get is
Root x. Okay. Okay. So we integrate this and
so
we
we get the expression as under root x by 2
get right.
from 0 to L is equal to root g into t.
Okay.
So the final time
Right.
turns out to be 2 under root L by g.
Whoa, which is a very familiar form actually.
Yeah.
Okay. So this is how you arrived at 2 under root L by G, which is something people are pretty familiar with. Although a lot of people are told to work this out slightly differently than this, but this is pretty much the analytical proof.
And one more thing, if you observe, there is no effect of mass on the time it takes to
correct.
reach the other end.
Just like in every oscillation concept that we
Yeah.
have come across till now or will come across later. So here again I'll summarize the problem. We were given a rope in fact of mass m and length l. So we proceeded to write the velocity as a function of x at distance x, starting from the bottom of the rope, and then we arrived at an integration which we solved and got the expression for time, which turned out to be 2 root of L by G. And this is something you'll have to use a lot later in other problems. So this is how you reach there. Okay, right.
Yeah.
So there was this error which we just corrected. The answer does not change because of that. So this was problem 4, and we'll move on to problem 5 now. Right, so we have reached problem 5. It says that the figure here shows an aluminium wire of length 60 centimeters joined to a steel wire of length 80 centimeters, and these two are stretched between these two fixed supports. And the tension produced in the string in the overall system is 40 newtons. And we have been given the cross-sectional area of the steel wire to be 1 millimeter square and that of aluminium wire to be 3 millimeter square. And we are asked what could be the minimum frequency of a tuning fork which can produce standing waves in the system with a joint as a node. So tuning fork is just what's something we use to ask frequency, because the tuning fork has to have that same frequency. And we are also given the density of aluminium and of steel. So how do we start with this?
Yeah. So problems of this kind, there is one very important tip which has to be understood.
Right.
That is, the frequency in both the media remains same.
Right.
That is the most important point which has to be applied in
Exactly,
this
and
problem.
we emphasized upon this point in theory
Yeah.
as well.
So first find out the velocities in both the media. So in velocity in steel, you get it as under root T by mu steel.
Right.
Calculate mu from the given density and the area of cross section.
Okay.
You get the velocity as 100 under root 2 by 39
Right.
meters per second,
Okay.
which is approximately 22.64
Right.
meters per second.
Correct.
Now calculate velocity even in the aluminium wire also.
Right.
Again similarly, T by mu aluminium, you get the same velocity,
Right.
which is 22.64 meters per second.
Okay.
And in the question there is one very important word which has to be noted, is what could be the minimum frequency.
Okay.
So for the minimum frequency,
We get a condition of the harmonic of the standing wave.
exactly,
Right.
for a given velocity and minimum frequency, the wavelength has to be maximum. And it is given that the length of the strings has 80 centimeters and 60 centimeters.
Right.
So for maximum wavelength, the distance between two consecutive antinodes has to be highest common factor of both the lengths.
Right.
Because see, you have this as
This
80
is a very, very
centimeters.
important concept in problem solving, in fact.
This is 80 centimeters and next this is 60 centimeters.
Right.
So if the distance between the antinodes is the highest common factor,
Right.
suppose the highest common factor of both of these is 80 and 60 is 20.
Correct.
You get 3 loops of this kind,
Okay.
and then here you get 4 loops of this kind.
Right.
So if you use any value other than this value,
Right.
these conditions won't be satisfied.
Okay. It will not be the minimum if you know.
Yeah,
if
it
any
won't
more
be the
values.
minimum.
Right.
So this has to be noted, and the highest common factor should be taken.
Right.
Here we are taking the highest common factor gives the right answer because the velocity in both the media is same.
Right.
If it is not same, then again you have to check and then satisfy the boundary conditions. That is, the displacement at both the ends is 0, and in the question it is given that even at the intersection the displacement is 0.
Right.
So based on that, the highest common factor technique is told in this problem.
Correct. And we use a highest common factor technique because it takes into account the fact that harmonics have to be complete in both the parts, and
Yeah.
highest common factor is just coincidentally happens to be a mathematical expression that summarizes that. Okay.
Exactly. So from distance between two antinodes, as we discussed, is lambda max by 2,
Right.
which is equal to 20 centimeters.
Okay.
So lambda max is equal to 40 centimeters.
Right.
So you know lambda and you know the velocity. From this get the frequency.
Correct.
V is equal to nu lambda.
Right.
This is max.
So
and
then
this
there
is
we
nu.
have nu is equal to V by lambda.
From this you get minimum frequency as 56.614 hertz.
Okay. So that was problem
5.
5, and we can see that we were given a composite system of two different materials, and we were told that it has the same velocity.
Yeah, based on the values, it turned out to be same velocities.
Okay, so since we saw it was the same velocity, then we moved on to finding the number of loops that will be there. The
minimum length between the maximum length between two antinodes.
Okay, so for satisfying that condition, we
Exactly.
found out that we can do that by taking the highest common factor, and then we realized that the number of loops here will be just 80 by 20. 20 is the highest common factor here of 80 and 60 in fact. So we'll have 4 loops here and 3 loops in the second string. So we found out the maximum lambda to be 20 centimeters. Okay, so from that we found out the
Minimum frequency required.
Again, so a couple of concepts here: the highest common factor concept when dealing with composite string systems, and then also the fact that for finding out the minimum frequency, you have to find the maximum wavelength, because they have a product relation to be constant.
And the most important thing is frequency in both the media is same.
Again, we will emphasize on this soon, again and again, and we did so in theory too, because all this information you need to start solving, and when you are sitting in a time limited entrance exam such as JEE or other such exams, you need to know where to start very quickly, because if you don't have that understanding, you will waste a lot of time going through the information in the question. So you have to have these basic concepts with you all the time, and you need to start making your assumptions very quickly soon after reading the question. So that was problem 5, and we'll see the next one now. Moving on with problem 6, the air column in a pipe closed at one end is made to vibrate in its second overtone by a tuning fork of 440 Hz. The speed of sound is 330 meters per second. Let P denote mean pressure at any point in pipe P, and P prime be the maximum amplitude of pressure variation. We have to find the length of the pipe, the minimum and maximum pressures at the open and closed ends, and the amplitude of pressure variation at the middle of the column. So it clearly says that it's an air column in a pipe closed at one end. That is a keyword. Also, it's in its second overtone. That is again a key, and to give us the frequency, they've given a tuning fork, which is nothing but just a way of conveying frequency. Also, the speed of sound is given, so we need to find the maximum and the minimum pressures at the open and closed ends. Obviously, this will not involve a huge expression. We'll just be using conditions which we know of. And in part C, we'll probably have to work with an expression because it asks for amplitude of pressure variation, in fact. Okay, so let's start.
Yeah. So let's pick up the first few keywords,
Right.
which are the second overtone, the closed organ pipe, and the 440 Hertz.
Correct.
So let's draw how the second overtone looks like.
Okay.
This is how it looks like with two closed loops.
So it'll have 2 nodes.
Yeah.
3 nodes, in fact.
It will have 3 displacement nodes.
Right.
And 1, 2, 3. 3 displacement antinodes.
Correct.
So from this is lambda.
Right.
And this is lambda by 4.
Correct.
So 5 lambda by 4.
In fact, that is lambda by 4 because we know that it will be undergo 1/4 of a full
Distance
oscillation.
between consecutive node and antinode is lambda by 4.
Correct.
So 5 lambda by 4 is the length of the organ pipe.
Right.
So we know the frequency of the tuning fork.
Right.
And we know the speed of the sound.
Right.
So from that we get the lambda.
Okay.
So lambda is equal to V by nu.
Right.
Substituting these, you get L as 15 by 16 meters.
Right. So now we have the length of the air column.
Yeah. Moving on to the B bit. First let's see for the open end.
Right.
At the open end, as we already know that it is a displacement node.
Correct.
But in the theory we have learned that the pressure function is lagging by pi by 2
pi by
radians.
2, right. Again, we did emphasize on that in theory. So the pressure variation has a phase difference of pi by 2. It actually
Yeah.
lags the amplitude by pi by 2.
So if the displacement is an antinode, the pressure is a node.
Right.
So there won't be any pressure variation at a node.
Right.
So the P dash
Mm-hmm.
at open end
Right.
is 0.
Okay, now an important concept there, an antinode in terms of the wave amplitude is also a node, in fact, in terms of pressure variation.
Exactly.
So it will always be 0 no matter what.
So P max is equal to P min is equal to the given mean pressure P.
Right,
This is for the open end.
correct.
And when you come to the closed end,
Mm-hmm.
for the closed end it is a displacement node.
Right,
But for pressure, since it lags
It will
behind
be
by
an
pi by
antinode.
2 radians, it is an antinode.
correct.
So P max
Mm-hmm.
will be mean plus the maximum variation.
Right, which is
And
P
s-
prime.
Yeah. And similarly P min will be the mean minus the maximum variation.
Right.
Now moving on to the C bit.
Again, in fact, one more concept that we need to look at, the pressure variation will be 0, but that doesn't mean the pressure there will
Exactly.
be 0.
Yeah. This is a very important point to be
Most
noted.
people, as soon as they find pressure variation 0, and 0 is usually one of the options, so that it's one of the common errors made. So we have to remember the pressure there is almost never 0. It will usually be the mean pressure.
Exactly.
Okay.
And then moving on to the C bit, we have seen that in a stationary wave, pressure varies sinusoidally.
Right.
The variation of pressure varies sinusoidally. So it can be written as delta P as a function of x,
Right.
can be assumed as P dash, which is the maximum pressure variation, into sine of kx.
Okay.
K can be found out from the lambda. We know lambda from the length.
Right.
So K is 2 pi by lambda.
Okay.
We get it as 8 pi by 3.
Right.
So your function delta P of x turns out to be P dash sine of 8 pi by 3.
Right.
Now it is asked for the pressure variation at the center of the pipe. So just plug in the value of x at L by 2,
Okay.
which is
So that will just simply give us
Yeah.
4 pi by 3L.
delta P is equal to plus or minus P dash by 2. And the reason behind putting minus is you have suppose this is the mean pressure line inside the organ pipe,
Right.
it goes to plus ones and then to minus ones.
Okay.
So I am denoting both the amplitudes
Right.
at a time in this.
Okay. So that was problem 6, and we saw that we were given again an open air column, open at 1 in fact, and we were given the frequency and the speed of sound, and we had to find pressure variation at all these 3 regions. So we noticed some important concepts here. First, that we have to determine lambda from the conditions given and equate it to L actually in some form. So from there we get the value of L because we know what lambda is. From then on, we proceeded to find pressure variation at open end, which will be a node, so there will be no pressure variation there. The pressure will always be the mean pressure. Similarly, at the closed end, we will have, since it's a displacement node, it will be a pressure antinode.
It will be a pressure antinode.
Right.
Yes.
So the maximum will be P plus P prime, and the minimum will be P minus P prime. When we came to part C, we wrote an expression for the pressure variation, and since it's obviously it won't be a function of time, so it's a sinusoid and sinusoidal function of x, in fact. And from then on, we proceeded to calculate the wave number, which came out to be 8 pi by 3. So we substitute that, and to find the variation in the middle, we substitute the value L by 2 for x. And from then we got the delta P, which is the pressure variation at the middle.
Yeah.
Okay, so that turned out to be plus minus P prime 2, and you just explained why the plus minus is there. Okay. Okay, so in fact it's P prime plus minus
It
P
turns
prime
out
by
to be
root 2.
P prime by root
Okay,
2.
this happens when we just plug the solution.
X as L by 2.
Right, x is L by 2, and you'll get P prime plus minus P prime by root 2. Okay, so this was problem 6, and let's look at the 7th one now.